Welcome back, everybody. And moving on to fall 2020. Fall 2020 roadmap. We're going to take these in order. Molecule NN comes from molecule PP, which comes from molecule OO. I had a little trouble reading what she's got here, but what she did was right. This is an example where we have a nitro group ortho to a leaving group. So if there's a good nucleophile around, you can do that rare nucleophilic aromatic substitution, also known as addition elimination. And you get this result. PP is here, and that's a cyano group where the bromine used to be. And I finally figured out that's a nitrogen she's got there, so that's cool. She did a reduction like she was supposed to with hydrogen in excess. That'll take the NO2 to an NH2 and a nitrile to a CH2, NH2, which is all good. Now I have a molecule with two amines, and I also have a preoccupation with amines reacting with aldehydes and ketones from chapter 16. It's a reaction that shows up over and over. If that's a primary amine, as it is the case with both of those amines, you're going to make imines when you react with aldehydes or ketones. And this molecule here is called oxalaldehyde. It's hard to say. It's a derivative of oxalic acid, but it's a reduced form. It's oxalaldehyd. And what happens is you get this result here in a condensation reaction. And what was your hint that it was a condensation reaction? And if you answered that Dean-Stark trap is a Stark hint, then you would be correct. So both nitrogens lose their H's and become doubly bonded to carbon in the oxalaldehyde. Oxalaldehyde look like this. And we have that. You'll have to excuse me for a second. Something's going on in the kitchen. It will not take long. We're back. So we have a double bond of nitrogen there from this carbon here, and a double bond from nitrogen here to this carbon here. This is the piece here. And that's NN. And now she wants to talk about S. So to get to S, let's look at what we have here. NO2, Br. Once again, you have a nitro and a leaving group, para. That's as good as ortho. So she correctly did the addition elimination to get the O attached to the carbon that used to have the halogen, which left. So also nucleophilic aromatic substitution. And then we're looking for somewhere to put a bromine with NBS, which is N-bromo-6-cinnamide. You'll need to look in chapter 8 for a review of that. And the favorite positions for putting bromines are allylic or benzylic. And in this molecule, I think you should be thinking about benzylic. That's a carbon one away from a phenyl. And you've got it. It's right there. So molecule T is this. And it's going to put a bromine there. And let's draw that. It's got, this is S down here. It's got an NO2 on top. It's got double bonds. It's got the benzylic carbon there. It's got an ether here. And the new group is a, let's see, it's a NBS. It's a bromine. So we're probably set up to do some substitution here. And what's going on here? A couple things went on here. Looks like we have, oh, I forgot my phenyl, didn't I? She's got her phenyl here. I just didn't read it properly. So that's a benzylic ether. And they're a little bit on the special side in that they can be cleaved with H2 and PT. You got to look in chapter 21 for hydrogenolysis. Hydrogenolysis. And that will generate your ether. Your ether will then become an alcohol, and you get toluene if you're curious. That's phenyl CH3. So you put an H on each side here. So that's one of those 3 points. Hey, won't H2 and PT take care of NO2 becoming NH2 as well? Answer, yes. How do you get a new oh, the new carbon's on here already. Got a new carbon on here. So how do you get an NH2 there? Now, a lot of you want to just do an SN2 with ammonia, NH2, NH3. I'm telling you, there's a section in the textbook called alkylation of ammonia. And it says it's not very good for making primary amines such as we have here, or secondary amines, or tertiary amines. It's only reliable for making quaternary ammonium salts. So you'd use an excess of this chemical with ammonia, and you'd get a nitrogen with 4 of these bonded to the nitrogen here. So right here, you'd have N with a plus charge and 3 more of those. Don't do that. We don't want that. A nice way to put on a carbon that has a leaving group an amine is to first react it with azide. So we're looking for reagents MM. Reagents MM start right here. If you use azide ion, and you can show off your SN2 skills and put DMSO or something here. I don't need a solvent, but it is an SN2 reaction. And then 2 H2 excess PT. Let's talk about all the things that does. It's going to do hydrogenolysis right here. It's going to reduce your NO2 to an NH2 up here. It's going to reduce your azide, which is N3 attached here, all the way to an NH2, and you get nitrogen gas. So I'm giving you 3 points for 2 steps because there's a lot going on in the second one. It covers everything. And there you have this product generated. And that's MM. Looking for Q. Looking for Q. Where are you, Q? Element OPQ. Sometimes it's just hard to find what we have. There's an R. There's an O. You probably know where it is, and I'm struggling. Yeah, I know how you guys feel on tests now. There's Q. We got to make P first. And hey, when I'm doing a phenol and you see a base and then a carbon that's allylic, you should be talking about Claisen rearrangement. The first 2 steps are setting up the Claisen. The next step is doing the Claisen with the heat. So she didn't want to know about P. I think she got P. Let's see, did you do a backside attack on this R stereo center and get an S stereo center? I believe she did. 1, 2, 3 is S. Nice. So this is the guy. I'm going to do just a little edit. There's nothing wrong with her picture at all. It's 100% correct. looking for my eraser. But when I'm doing Clason's, I need the resonance form where the double bond is showing there. It's just the other resonance form of the structure she drew. I really didn't change anything, because then I can do the arrows. And the arrows say, you go to the distal end of the alkene. Oh, that's not a nice arrow. There, you hit tack there, and this resonates up here, and then this becomes a pi in here. And you get a carbonyl intermediate, which will sneak underneath here. A little big. And it's the intermediate. It's not molecule Q yet. You get a ketone. And no, the ketone's not there. Oh, so harsh. Ketone's on top. Sorry, I rotated her molecule, confused myself. And then on the alpha position, you have this new bond. Don't forget you got a methyl down here. It's got a new bond there to a carbon that has 2 methyls on it. Well, that's a little large. And goes to a C that's doubly bonded to a C with a methyl there. There's double bond there to a C that has a methyl. And that's the intermediate. It undergoes tautomerization to Q. This is a tautomerization that favors the ene. I know, I missed a double bond. I'm putting it there now. There we go. And sometimes tautomerization favors an ene instead of an ene, a ketone, a carbonyl. And the reason why is this one's aromatic. And there is Q. And there, Q. And where else are we going? Does she want H? Yes, she wants H, of course. H is not as tricky as you might think. What's happening is, let's see, we got the bond to the dimethyl. We got this bond here already, so I'll put it in red. You don't have to make it. You already made that bond. It looks like this carbon right here has to end up attached to the benzene down here. So how could you make that into an electrophile and do an electrophilic aromatic substitution? It's an alkene. I can make a cation there. That's all I need to do. Make a cation right there, which is there. And that would just be HCl or H2SO4 or H3PO4. Some kind of strong or moderately strong acid. So H would be that. I'm pretty flexible. If you give me anything that's strong or real close to strong, I'll even take sulfuric acid if you want. And that gives you this ring. You get a cation here. This will attack it. It's the only carbon that can really reach is this one. This one's too far away. So this one will reach over there. You get a nice cation down here. It's beautiful. And then you do your electrophilic aromatic substitution mechanism. And we did H. U. There's U. U is going to oxidize with heat. Oh. Yeah, you don't see an alcohol, so you're saying, I don't know what to do here. Well, there's no alcohol. What's chromic acid going to do? Yep, this combination gives chromic acid. But we also remember that chromic acid with heat will oxidize a benzylic carbon that has at least one benzylic hydrogen. So there's a benzylic carbon here with no hydrogens. Can't oxidize it. Here's a benzylic carbon with 3 hydrogens. You only need 1. This will become a carboxylic acid. Where does one find this reaction? end of chapter 21. So when we're talking about molecule U, chapter 21, benzylic oxidation. And you're going to get CO2. It's ignoring me. What did I do to deserve this? Oh, I was touching the screen with my other hand. Should know better by now. U. And that goes, that's the former CH3 right there. And O2 there. No change down here. It's already oxidized. There's your U. And then U is going to react with M to create a scenario where we have both an ester. That would just be a Fischer esterification. Fischer esterification looks like we're making an ethyl ester there, doesn't it? ETOH H2SO4AQ. Not a, oh no, not a, the opposite of AQ. What is the opposite of AQ? DST. Get rid of water. Don't add water. So that would be step 1. And step 2, what else has to happen? You have to reduce a carbonyl all the way to a CH2. You have to go to chapter 16 for that. The reason we learned it in chapter 16 is so we could use it in chapter 22. Notice we put on a ketone earlier in the sequence. You had no trouble with that. The only way to get a primary R group onto benzene is to reduce a ketone to a CH2. The Wolff-Kishner is a good one, although I'm worried. Wolff-Kishner conditions have hydroxide and water, which could also do saponification of an ester. I don't want that. I need the equivalent of the Wolff-Kishner that doesn't do saponification. It's called the Clemenson, also found in that same section where we did chapter 16, Wolff-Kishner, chapter 16, Clemenson. You need HCl and zinc alloyed with mercury, also known as zinc amalgam. So if you're stressing out and by mistake you use the Wolff-Kishner reagents, I'd probably give you 3/4 of a point because you knew what you had to do, but you forgot that an ester will undergo saponification with hydroxide and water. So that's M. We're here. And XYZ. XYZ. We're into chapter 23 here because I have an amine. I think her prediction for W was good. What she did was we made an imine with an aldehyde, as we did way back here. We made 2 imines with 2 aldehydes. And then she reduced the imine to an amine with hydrogen and platinum. So we set it up for what's called the Hoffman, what am I calling this? It's a Hoffman rearrangement? No, it's the other Hoffman elimination. So let's just break it down here, okay? Step by step. Separate U out from, I got my pen. Separating U out from this story here. So step 1 from here with excess methyl iodide gives us the phenyl. I think I can go with phenyl. CH2C with a methyl, N with no more hydrogens and a propyl. She's got 2 new methyls on here. And if you look at all the videos and in the textbook, step 1 is called exhaustive methylation. Get as many methyls on there as possible. And this is a quaternary ammonium salt. Step 2, the iodide anion, which is a spectator balancing this cation, is now replaced with a hydroxide. Yeah, step 2 generates hydroxide, and you need to know that mechanism. And hydroxide's a base for the elimination. We'd have to do a little bit of a search and finding beta H's. Those are your candidates for elimination right there. Oh, I got another one. Three candidates for elimination. Hey, 3 products. Coincidence? No. Each XYZ is a pair of an amine and an alkene. All right. So if hydroxide grabs this H, it makes an alkene here and this leaves. If hydroxide grabs this less hindered H, it makes an alkene here and this leaves. And with the Hoffman elimination, it's all about taking the least hindered H. So major, supposed to be X. Take this alpha H, make a double bond there, and this leaves. So you're going to have this major product. It's a product combination. Leaving group is here. So that is X. Y. Let's see. I don't want it getting too wide. I don't want it getting too tall. Y, I'm going to just, it doesn't say we have to distinguish minor from most minor. So I'll just go with down here. I'll make a double bond there, and this will leave. So it'll have the same amine here. I don't know. Would it be too presumptuous if I did this and say they share this amine? I mean, it's getting a little creative, but that would be a double bond here, right? And there. So Y is a combination of this and that. And Z is an independent entity all to itself. It comes from taking this H here. You generate a pi bond there. So you get a pi bond from there. And you get this whole top part leaving. Where am I? I'm there. There. And that's Z. Z gets its own color. Gray. Okay. I think we covered that a little longer segment there for sure. And we'll be back, a little preview of what we're coming back for. And here it is. We're over here. And it looks like we have 2 fairly short questions. And I'll see you shortly. But I do remember something about page 1. Did we finish page 1? I think I might not have. Yeah, I put. Yeah, we talked about page 1. Sorry. I'm going to come back with those 2 short questions, page 3. If it lets us look at them. There we go. See you soon.